Hello everyone, so we are going to start part 4 from the topic Coarse Dispersion. So in this topic, actually we are going to discuss some of the electric property of the suspended particles in the suspension, or you can say Coarse Dispersion. How this electric property they contribute towards the stability of the suspension, we are going to discuss in this particular class or in this particular presentation. So without wasting any time, let's start our presentation. You see, first of all, Brownian movement. So what is Brownian movement? So earlier we have already studied Brownian movement can be defined as the random movement of the particles, right? So Brownian movement of a particles, it generally helps in the case of sedimentation. The Brownian movement prevents the sedimentation of the particles, suspended particle in a suspension, by keeping the dispersed material in the random motion. The dispersed material, they will remain in the random motion, and thus this random motion that prevents the sedimentation of the particle. So the Brownian movement depends on the density of the dispersed phase, how much the dispersed phase it is present in the suspension. Moreover, it also depends upon the density and the viscosity of the dispersion medium. But the thing is that you should know that the kinetic bombardment of the particles, means the random movement of the particles, that is of the dispersed phase of the particles by the molecules of the suspending medium, will keep the particles suspending. But the thing is that the particle size should be below the critical radius for Brownian movement. If the particle size it is greater than the critical radius value, then the Brownian movement doesn't occur in case of the suspension. Now let us discuss regarding the electrical properties of the interfaces. So first of all, I would like to brief the concept here in this chart. Then afterwards, every time you have to just keep the relationship with this particular graph. See, suppose this is a solid surface of the suspended particle. Now, if the solid surface of the suspended particle, if it acquires a positive charge, if it acquires a layer of positive charge above it, this layer from where it has come? This layer of positive charge has come from the dispersion medium. Now, this layer it is designated with A and A prime. Now immediately to this we will have one negative layer. Why? Because this positive will bring the negative charge close to them. Now where this negative ion will come from? This negative ion will also now come from the dispersion medium, right? So immediately next to this positive charge, the tightly bound charge, there will have one negative layer. So these are also known as the counter ion, or they are also known as the Gaussian ion. Now at a particular distance we are going to have another layer. This is designated as B prime. So this layer it have a positive charge. This is just opposite to the counter ion. So they will have a positive charge. Next to that we will have a negative charge layer. Then again we will have a positive charge layer. So this is the C prime, and finally the next it is the D prime. So the first distance, that is the distance from A to B, it is the distance, or this is layer, it is known as the tightly bound layer of the electrolytes. So this is the tightly bound layer of the electrolytes. Whereas the B to C, it is known as a diffusion layer. B to C, it is known as a diffusion layer. And lastly, the C to D, it is known as the electroneutral region. So this is the electroneutral region. Now electrical properties at the interfaces. So electrical double layer, how it forms. Suppose here again I am saying the same thing. Suppose let us consider it as a solid which is in contact with the solution of the electrolytes which contains the ions. Now what will happen? As discussed earlier, some cation will get absorbed at the surface of the solid. These are the cation, they will get absorbed at the surface of the solid. This is shown by A prime, right? Now what will happen? The absorbed ion that gives charge to the A prime. Now it is this adsorbed ion, this ion layer, it is also known as this A prime, it is known as the potential determining ions. I repeat, the charged particles at the A prime, it is known as the potential determining ions, right? Now the ions attracted to the positive charge by the electrical forces. These ions, which are shown by the B prime, these are known as the counter ions or the Gaussian ions, as we have already discussed in the previous slide. Now this layer B prime, it is actually, see, this is the shear layer. B prime, it is a shear layer rather than the A prime. Why we call the B prime as a shear layer? Because why? The shear plane is B prime, then the A prime, because of the tightly bound layer. This is because of this layer is tightly bound. So this is known as the shear plane. Then we have the first layer is actually A prime to B prime. This is the first layer. The next layer it is, the second layer it is the B prime to CC prime, right? Now the concept Nernst potential. What is Nernst potential? Simple, you see, the potential at the solid surface, the potential, if we put one electrode here, the potential at the solid surface due to the layer A prime, right? A prime, this is also known as a potential determining ion, right? It is known as the Nernst potential. The potential at the solid surface at the A prime, and this potential has come due to the potential determining ion. So this layer is known as the, or this potential, it is known as the Nernst potential. This is the Nernst potential. Now it is defined as a potential difference between the actual layer and the electroneutral region. This is the electroneutral region. So if we put one electrode here at a tightly bound layer and one electrode here, the difference between this voltage, it is the Nernst potential. Clear? The next concept, it is the zeta potential. So what is zeta potential? See, zeta potential can be defined as the difference in the potential between the surface of the tightly bound layer, that is the shear plane B prime, and the electroneutral region, that is the D prime. So the zeta potential, it has a practical application in stability of system containing the dispersed phase. We know that because the more is the zeta potential, the greater is the magnitude of the zeta potential, the more stability is the you can say the suspension. Now if the zeta potential is reduced below certain value, if we reduce the zeta potential below the certain value, what may happen? Then attractive forces between the particle will exceed the repulsive forces. If we reduce the zeta potential, then the attractive forces will exceed the repulsive forces. If the attractive forces will exceed the repulsive forces, what will happen? The particle will come close to one another, and this phenomenon is known as the flocculation, right? So the flocculated suspension is the one in which the zeta potential, it ranges from -20 to +20. So if the suspension have a zeta potential value of -20 to +20 millivolt MV, then the suspension is said to be flocculated suspension. So thus the phenomenon of flocculation and deflocculation depends upon the zeta potential carried by the particles. Now if the zeta potential is more than -20 or +20, then it is a deflocculated suspension. So this is the electrokinetic potential. You can see here, this is the potential and this is the potential difference. So this is the tightly bound layer, this is the diffuse layer, and this is the electroneutral region, right? And this, the B prime, is known as a shear plane. The B prime is known as a shear plane. So if we take one, put one electrode here, another electrode here, right? This is the electroneutral region. This will give you what? This difference will give you the Nernst potential. If we put one electrode here in the shear plane, another electrode in the electroneutral region, it will give you the zeta potential, right? The next thing, it is the Dlvo theory. So it has been given by few Russian scientists in the year 1940, and this word Dlvo, it has come from their initial of their name, Dlvo. I will show you how. You see, it has developed in the year 1940, right? All by the Russian scientists. This is the D, Darjaguin, this is the Landau, and two Dutch scientists. One it is the Verby and the one it is the Overbeek. Right? Now what this theory states, as per the Dlvo theory, it has proposed that an energy barrier resulting from the electrostatic repulsive forces, it prevents two particles approaching one another and adhering to one another. If two suspended particles, they come close to one another, they may get coagulated, right? But as per the theory, there is an energy barrier, which energy barrier means the repulsive forces, which prevents their coagulation or aggregation, right? So if the particle collide with sufficient energy, now still if the particle collide with sufficient energy to overcome the barrier, means to overcome the repulsive forces, then what will happen? Then the van der Waal attractive forces will attract them strongly and cause them to adhere together irreversibly. Thus you see, if the attractive forces supersede the repulsive forces, then finally the adhering of the particle takes place. So if the particles repels each other strongly, the dispersion will resist the coagulation and the dispersed system will be stable. I repeat, if the particle repel each other very strongly, then the dispersion will resist coagulation and finally the particle will remain suspended and the system, it will be stable one. So if the repulsion is not sufficient, then coagulation will take place. As if the repulsion is less than that of the attractive force, then coagulation will take place. So this is the chart, this is the interactive energy, this is the positive and negative side. So this is the charge repulsion, you see, combinedly this is the energy barrier, this is the van der Waal attraction, this is the charge repulsion. So this is the distance between the particle. If we increase the distance between the particle, both will become less, but if we increase or if we decrease the distance, if we go this side, you see both their magnitude increases. The magnitude of the repulsion also increases, the magnitude of the attraction also increases. So it is also shown in here. So it is the, you see, unbound particles, they form the reversible, or you can say reversible chaining, means they will come close to one another but they will not adhere. But if the distance is less and if the van der Waal forces of attraction supersede the charge repulsion, then therefore they will form the primary union, or it is known as the primary minimum, means they will attract to one another or they will adhere to one another irreversibly, means it is very hard to divide them afterwards. So thank you everyone, hope you have liked the video. If you like the video, just press the like icon, you can share this video and you can subscribe to my channel. Thank you once again.